Good afternoon, everyone, and welcome to the DEMAP seminar. Our today's speaker is Yoshiharu Kohayakawa. He did his PhD in Cambridge in 1991 with Professor Bela Bolubash, and at the moment he's in the University of Sao Paulo, and he works on different aspects of graph theory and combinatorics, including random graphs, regularity lemma. In 2018, he got a Fulkerson Prize for his work on chromatic thresholds in graphs. And today, it's a long title, so it'll be something to do with Beampacking and some games. Please.
Thank you very much, Oleg. Thank you very much, Romanujan, for the invitation to speak in this series. So I'm very happy to talk to you. Thank you very much for the people who are listening or watching. Right, it's a long title, but I will try to explain what this is about. Right, so the talk will have three parts. First, I will talk about the Beampacking problem. Namely, I'll talk about Beampacking the following version. So bounded space online, and it will be about D hypercubes. So I'm interested in high dimensions. Now, this Beampacking problem is kind of related to there's a game-theoretical version of it, which is this selfish D hypercube Beampacking game. So I'll speak a little bit about that. And at the end, I will try to give some proof components. In particular, I will try to talk about a certain packing lemma in D dimensions, packing of D hypercubes. Okay, so let me start with Beampacking. So Beampacking is a classical combinatorial problem, combinatorial optimization problem. So you have n items, so x1 up to xn. So these are just real numbers between 0 and 1. And you have recipients, you have bins. So these are just the unit intervals. And the aim is to find a packing of these x1, x2, and so on into as few bins as possible, unit intervals as possible. And that means the following. You want to split the items. So maybe you want to split the set of indices into blocks, into parts, P1, P2, and so on. And of course, what you want is that in each part, so part Pj, if you add up the stuff that you put in Pj, you add up that most one, because the bin has capacity 1, it's a unit interval, right? So the xi that you decided to put in Pj have to fit. And again, you want to minimize the number of such bins, Pj, number of parts Pj. So this is the classical Beampacking problem. Now, I'll be talking about a higher dimensional version. So here's the 2D version. So now the items are no longer reals. They are rectangles or squares. Actually, I'll talk about squares, but anyway, so they could be rectangles. And the bins can also be rectangles and squares. Again, I will restrict myself to hypercubes, or squares in 2 dimensions. And lastly, I will be interested in packings, which I call orthogonal packing. So packings as the one that you see below. So the rectangles that you are fitting into a bin have to be either horizontal or vertical, if you see what I mean. So things like this are not allowed, right? So you cannot tilt your squares or rectangles that you want to fit into the bin. So again, you want to, so again, the problem, the 2D Beampacking problem is as follows. You receive as input a set of rectangles and some unlimited number of identical bins where you want to put these items. Okay, so task is to pack the rectangles, the items, into the minimum number of bins. Now, of course, if you rescale your units in the X direction and in the Y direction, you can assume that the bins are unit squares. But still, in general, you could have rectangles as items. Okay. Now, there is motivation to do this in 2 dimensions, or perhaps even high dimensions. So you could think of a process. So this blue thing in the bottom that you see, well, there's a P inside. It's a process, and this process takes up m memory, m units of memory, and let's say it takes time t, little t to finish. So you could have many processes described like that, and then you would like to use, you'd like to kind of execute this family of processes, distributing them into as few computers as possible, right? And each computer has some capacity for time and memory. So there is some kind of motivation. But this is all I will say about motivation. I will just consider it as a kind of a mathematical problem. Okay. Now, I said that in general, the items could be rectangles, but I will restrict myself to squares or hypercubes. I will not talk about parallelepipeds, right? So everything will be hypercubes. Okay, and I'm particularly interested in high dimensions. Now, so far I just talked about beampacking and high dimensional beampacking, hypercubes. But now I'm interested in a particular variant, namely I'm interested in the online version. So that means that the items arrive online and they must be packed right away. So that is the first restriction I will impose. Now, let me see whether this works. Right, so that means that you get the items. Oh. Just a second. Oh, I'm sorry. Okay. Right. Sorry. So you have these items that arrive, and you must pack them right away. I'm having some little technical problem here. And also you have this bounded space condition. And the bounded space says that at any point, the number of open bins is fixed. So I want to, it would be good if I could.
I think I saw this problem that somehow some people couldn't draw. Yes. Oh, now you can.
I know, no, it's working. Right, thank you. So, okay, so I have these items and they arrive and I have some bins. Maybe I kind of decide to put this here, but then for some reason I decide to put this here. The items are arriving this way, right? And the next one I decide to do this. So the online means that I have to decide where, so this is the next item. So I have to decide where, in which bin I want to put it. So right away, I cannot change my mind afterwards, right? Okay, so maybe I decide to put this item here. Now, so this bounded space thing is the following. So currently I'm using these two bins to put the items, right? And this number has to be bounded by some constant n. In other words, so for instance, let's say I have the next item, and for some reason I want to put in some new bin, then I would have 3 and my bound is 2. So what I have to do is to close this bin. So I have to deliver this bin saying, well, this is done, and I will not put more items into it. And now I have, again, I have 2 bins in this example. So the number of open bins, the ones that are still accepting items, has to be bounded. So this is what I mean by bounded space. Sorry, that's not what I want to do. This is what I want to do. So that was the online bit, and this is the bounded space bit. And of course, you want to minimize the number of bins that you use. Okay, so I'm interested in this version, online bounded space. Now, we are interested in algorithms for this problem. So given an algorithm A and given a list L of items, so it's a sequence of items, right? I'm interested in proving bounds of the following form. So AL is the number of bins that I use. I want to prove bounds of the form alpha times the optimal value for L plus beta, where this optimal value for L is the offline optimum. So it's the stuff that's written just above here. In other words, if you knew L in its entirety and you had infinite power, you would compute the best way to pack this list L of items into bins, right? And the number of bins that you use in this best possible kind of scenario is opt L. So I would like to say that AL is not more than alpha times worse than opt L. Now, I also allow this beta here, simply because I'm not interested in small instances. I'm interested in instances or lists L that have large optimum. So I just allow some constant to avoid problems that arise in small instances. And the aim here, of course, is that in this equation 2, I want alpha to be as small as possible. And I allow beta to be big but constant. Okay, so yes, sure.
This alpha in equation 2 and this lim sub, this is the same constant, right?
Yes, yeah, right. So one is kind of maybe some more formal way of writing it, but what we really want, let's say it's 2. You want to bound, you want to find the best alpha for your algorithm. And then that alpha is the quality of the algorithm, is this R infinity of the algorithm. Yeah, thanks. And of course, this is about a fixed algorithm. Given a problem pi, what you want is to find the best possible algorithm for it. That means you want to find the best A, which has the smallest alpha, or infimum of the possible alphas. So that's the difficulty of the problem pi. And we have one problem. We have this online and bounded space D hypercube beampacking problem. So this problem has some difficulty, R infinity. And Epstein and Van Stee in 2005 wrote a very nice paper about this. They were able to find an algorithm which they can prove abstractly that it's optimal. And they could estimate this R infinity for this optimal algorithm, and they proved theorem 1. So they proved that this alpha, this quality, is between log D and D divided by log D. But this optimality of this alpha, they could compute, they formulated it as some optimization problem, and they left open, where it actually is in this interval. And they believed that you could do, that the algorithm would give log D. So this problem is not more than log D difficult, let's say. That was the problem of conjecture. Okay, so we were actually able to prove that the problem is more difficult. In other words, you are at the other extreme between D and D over log D. This R infinity is D divided by log D. But since they already proved from above the D log D bound, so you know that this problem has R infinity D divided by log D. So this is the main result. And later on, I will try to give some idea of the proof of this lower bound. Okay. Let me move on. So now we kind of change the subject. Now let me talk about this selfish beampacking game. Now, again, you see in the picture above, you see 3 bins and rectangles, so packed in them. Now let's think that each rectangle, so each player controls one rectangle, or you think the players are the rectangles. Now each player has to pay for the space that it takes up. So look, for instance, at this middle bin and this green guy. This green guy has some area, right? So it pays for its area. But not only that, since this green guy has 2 other blue mates in the bin, they share the cost of this bin. So this bin, let's say, costs 1, right? but the green and two blue guys share the cost of this bin. So that you could divide the cost of the bin by 3, that would be one measure. But the measure I will use is the following. So the guys pay proportional to their area. So that means that the green pays this expression 8, so its own area, divided by the total occupied area. So if this green was the same size as the two blues, each one would pay 1/3. But since this green is smaller than this tall blue guy, it will pay, I don't know, maybe half or 2/3 of this blue guy, right? So they pay proportional to their area. Okay, so that is the cost that this green guy pays for being in this bin. Now, we think of these rectangles as players, and this green guy is kind of watching where it could go to pay less. So for instance, so the green guy now could consider moving to the 3rd bin. Now, clearly in the 3rd bin, you have a much bigger occupied area. So the green is kind of a smaller proportion of the occupied area, right? If green moves there. So green ends up paying less. So it's a good move for green. So in this game, so it is the 3rd bullet point. So the rectangles selfishly move to any bin that they find is better for them. So that's the game. So is it clear? So every rectangle is looking for places to go so that they pay less. And the cost is given by this expression 8. Okay, so this selfish bin packing game, this variant, this and other variants were introduced by Paulo. Right, okay. So let's see. So I'm really only interested in this. I want to know whether the rectangles in a certain configuration are happy, each one is happy, or there's somebody somewhere who would prefer to move. That's the only thing I care about the packing. Now, so given that incentive, or given that definitions of cost, we can define the Nash equilibrium for this game as follows. We say that a configuration, such as a pack, like the packing that you see at the bottom of this picture of the slide, you say that you have a Nash equilibrium if no player, no rectangle, has any incentive to migrate to any other bin. So in theory, this is an example of an equilibrium. So for instance, so you could think of this item C here, the light blue. This guy, of course, could move to 1, but then he would pay more, right? Clearly, kind of. Right, so it does. So C is happy to be there. And we would have to check this for every item here in this picture, that each item has no incentive to move anywhere else to reduce its cost. Okay, so in theory, this is an equilibrium, but let me not move so much. I mean, we would have to check for all the items that are here, and I want to do that. I won't do that. Okay, now, so given a packing, you call the social cost of the packing the number of bins that that packing is using. And the optimum is when kind of all the items, all the rectangles kind of discussed globally, and they fit themselves in the best possible way into the bins. So this is the optimum where the society works together. Okay, so you have this, or maybe I should say one more thing. Right, so for any packing, there is a cost, and that is the number of bins. And ideally, you would want society to work, everybody to work together to achieve this social optimum, right? But now we have these selfish guys. So for instance, maybe you have this packing in the first row, right? But then if you look at the second row, you see that, let me see, item A, this light green on the right, moved to bin 2. Well, it did that because that way A pays less, right? So the rectangles, the players now can move And so from the second row to the third row, what happens is that B realizes that it would pay less if it moves to bin 3. So that is what it did. So it's paying less. Now E here, which is paying 1 at the moment, if it goes to 1, it will pay less than 1, right? Because there's this mate J in bin 1. Okay, and we achieved, so the game evolved to the situation. And this happens to be a Nash equilibrium, or we're saying it's a Nash equilibrium. And what happened is that this game evolved, and you ended up in this situation which will not change because nobody has any incentive to move. But it so happens that these guys can fit into 2 bins, like in the picture at the bottom, right? So what happens is that in the Nash equilibrium, you are paying 3, the society as a whole is paying 3, using 3 bins, but they could achieve 2. So that's the price of anarchy, or a lower bound for the price of anarchy for this instance. These guys achieved 3 bins, but they could have achieved 2. They didn't achieve 2 because they worked selfishly, right? So the society here is anarchical, and that is what happened. So the price of anarchy is at least 3 halves for this instance. Now, so this was a particular instance, but then you could again ask how bad this quotient can be. So you could ask, what is the cost of the worst Nash equilibrium? So it's the numerator of this fraction in 9. And the social optimum is the best that this society could achieve working together. So this ratio here is how much you pay for this, for the anarchy, right? For the selfish players. And again, you're interested, given this game, you're interested in estimating this quotient, how bad this can be. So again, we can write this problem as in the inequality here in the second bullet point. So you would like to say, oh yeah, this game is not so bad. The worst Nash equilibrium has value, number of bins that you use, is at most alpha times optimum. Optimum, again, of course, is the social optimum, is the number of bins you need if they work together. And again, you have the same expression. It's alpha times this best plus some beta, which is some constant. So again, we want to get rid of small instances. And you call the price of anarchy of this game the best alpha that you can achieve in this inequality, right? So this is the price of anarchy of this game. Now, so you can prove kind of the same packing lemma that I will discuss soon. Implies that the price of anarchy of this game is at least d divided by 5 log d. So it's again a lower bound of order d divided by log d. Now, in the previous case, this lower bound of d divided by log d was good because we had a matching upper bound, right? So Epstein and Van Stee proved, found an algorithm that achieved this, had this quality of d over log d for the problem, for the online bounded space problem. But in this case, for this game theoretic version of the problem, this lower bound in 11 is not so great, at least we don't know, because the only upper bound we know is 2 to the d. Is not difficult to prove, but anyway, so we have this large gap. Actually, I think it would be nice to close this gap. And it's a very big gap, right? So maybe this is a good problem. Okay, so this is the second main result, and now I will try to talk about the proofs a little bit. And to talk about the proofs, it may be better if I go here. Right, so for the proofs of these theorems, we need these homogeneous packings. So the idea is that I will have cubes. So this is 2-dimensional, but in general, I have qk, maybe of dimension d. And these will be cubes which have side length not half, 1 over k plus a little bit. So maybe like this, right? So for instance, here you see the case k equals 2, and it has size slightly more than half, side length slightly more than half, right? So in this unit bin, you can only fit one of them. So you can only fit one Q2. Something similar happens here. Q3 has side length 1/3 plus a little bit, so you can only fit 4 of them, right, in 2 dimensions. And the same thing, you see the same thing everywhere. Anyway, so I'm interested in these packings of cubes of this form into unit bin. And again, let's just remember that all of them, in any case, I can fit at most this many of them, k minus 1 to the d. Okay, so these are homogeneous packings. So the packing lemma is the following. So for every d bigger than some d0, so in high dimensions, you can pack this many. So 10 over 11 k minus 1 to the d. Remember that in these homogeneous packings, I have this k minus 1 to the d, right? But now I have 10 divided by 11 of them. So you can pick 10 over 11 times this maximum k minus 1 to the d of these qk's, of these guys, right? For all these values of k, and I can pick them simultaneously into one single unit bin. Right, so I'll try to save this again using the picture of the previous page. So here, too much here. So let's see. So in this case, when you take 10 over 11 of 1 is 10 over 11. Here again, you have to take 4 of them. Here, I think you have to take all of them. Here you have more than 11, so maybe you can like that. But anyway, so the claim is that you can pick a fraction of 10 over 11 of all these guys, right? And you can do this for k's 2 up to some value s, which is of the form, of course, the coefficient is not so important. It's of the form d divided by log d. So you have a bunch of these qk's, right? Some number of q2, some number of q3s, up to some number of qs's, and you can pack all of this into one unit cube, into one bin. So that's the claim, right? Okay, so this is a little bit kind of a little bit surprising, because if you think of these homogeneous packings, it looks like they have good occupancy, right? So this guy here is quite a lot. So if you just remove 1 over 11 of these things, they don't seem to kind of fit, right, in one, just because you don't have enough area in one unit cube, in one bin, right? But of course, the point is that you see high occupancy in dimension 2, but if you have large d, you have small occupancy, right? So for instance, here you have occupancy 1/2 raised to d. So the point is that in high dimensions, these guys are not so much filled. But anyway, so this is the lemma. And to prove that all these cubes fit into one bin, you can use the probabilistic method. So maybe I will be able to say a little bit about it, but we'll see. Now, so we want to use this lemma to prove that there is some bad Nash equilibrium, and we want to use this lemma to prove that there is a bad instance for the online bounded space Beampacking problem. So let me start with the Nash equilibrium. Okay, so you take this homogeneous packing. But in this homogeneous packing, I have only one of these guys with k equals 2, right? One for k equals 3, and so on. But maybe you can, so I could do the following. I could increase the number of any of them. So I could have not one of this, but I could have 10 of this. Here I have one, but I could have 20 of this packing of Q3, right? So I can just, so this is, what am I saying? I'm saying this thing here. I can combine any number of these individual homogeneous packings in any way, and I will always have a Nash equilibrium. What does that mean? That means that no cube here, so or no square or no cube, I'm not sure. So this guy here has no incentive to move to the left. This is a small calculation, right? You just have to check that if this guy moved to somewhere to the left, it would pay more. Yeah, this is some calculation you have to do. And just geometrically, it's clear that some guy, so this guy has no way to move to the right. So the only move possible here, the only possible moves are moving to the left, and when you move to the left, you pay more. So this is a Nash equilibrium. So this is this fact here in the bottom. Now, so, and we want to say this is a bad Nash equilibrium. So we want to show that if these guys work together, they would fit in some smaller number of bins, right? So let me see. So I'm talking about this. We have this packing lemma, and out of that, I would like to prove a lower bound for the price of anarchy. Remember, price of anarchy is the ratio between worst Nash equilibrium by the optimum. Right. Okay, so here's the kind of idea of the proof. This is supposed to be a Nash equilibrium. Oh, this is a Nash equilibrium. And the right-hand side is not optimum, but the optimum is, how do I write? So the number of bins I have on the right, bins here, is an upper bound for the optimum. So, okay, let me see. Let me try to explain what I mean here. I said that you could take these homogeneous packings and duplicate or triplicate any of them, right? So here I will have some number. You see, I have some number of these packings of Q2s. Here I have some number of packings of Q3s, and so on, right? I will tell you soon how many of them. But to do that, I have to go back to the lemma. So here's the lemma. So this lemma claims that some family of these special hypercubes, QK, can be packed into a unit bin. So let me call this packing U. So this packing U is like this: is a unit bin, and you have a bunch of these QKs in it, right? So I have U here on the right, and I have question marks because I don't know what they look like. So anyway, so but it's the same packing several times. The number of times I have here is n, where n is the following: is the product over k of new k okay, and what is new k? New k is the number of qk in U. So this U contain these qk's for several k, and I count for each k how many of them I was able to fit into this packing U, right? This U contains several of them, and I just count. Good. Then I have this number here in the bottom, this product of these frequencies of the qk's. Now, also let me define the number. Let me also define the number nk hat, which is this n divided by new k. Here I do this, I just 2 hat 2, well, actually, paper. This is this 2 to the d, 2 square, 2 to the d. So in general, I have n k hat, k minus 1 to the d. Okay, so how many copies of this homogeneous packing I put here in this row? I put this many. So it's 2 to the d because I have 2 to the d guys in each individual packing here, right? And I multiply by this number n2 hat, which is at the bottom of the page. Anyway, so I'm specifying how many copies of each of these guys I put in each row. Now the key thing, it's actually just the following thing. On the right-hand side, I have big N copies of this packing U. So if you ask how many QKs I have in total on the right, that is easy to compute. It's N times nu K, right? And you just check that on the left, you also have this number of QKs. It's very easy, right? So you just have to multiply this number here by, so this is the number of copies of this packings, and each of them, oh, maybe I got it wrong. Sorry, maybe I got it wrong. This is nu2. It's good that I try to check. Right, so again, I have 1, 2, 3. How many? I put this many. NK hat nu K. How many QKs I have in total? Well, this number multiplied by K minus 1 to the D. Okay, that is this number here on the right also. So on the left and on the right, I have the same number of each of the QKs. Okay. We already claimed that on the left you have a Nash equilibrium. On the right, I have these packings. So the cost of this is what? Is the number of bins I have on the left divided by big N, right? So this calculation is, so on the left, I said you have NQ hat nu K copies in each row, and you sum over K, right? And it's this divided by N. Okay, so I divide this by K minus 1 to the D, K minus 1 to the D, and then this times this is equal to N. So I cancel, and therefore I get the following. I have nu K raised to K minus 1 to the D. Now, the lemma said that I can pack, so how many QKs I can pack? I can pack 10 over 11 K minus 1 to the D. This packing U have this property. So in other words, this number here is at least that much. Great, so that means that this ratio is some constant, 10 divided by 11. So it's just now a matter of recalling how many Ks I have. We were able to get, this was S 10 divided by 11. So what is S? Is the Ks that I could put in the fit in the lemma. So let me see. So where is the lemma? Sorry. Where's the lemma? Again, the lemma said that I could fit for each of these Ks, 10 over 11 K minus 1 to the D QKs, right? So that summation involved this 2D over 9 log D values of K. Right. I hope that gave some idea of how this calculation goes. right? Now, to produce a better instance for the online bounded space Beampacking problem, you kind of look on the left and you produce a list of many Q2s. How many? Well, as many as you see in the picture on the left in the first row. Then you put several copies of Q3 in your instance.
Sorry,
How
Yoshi.
many?
Can
Yes.
you start again what you were explaining now? I missed.
Right. Yes, I'm sorry. Yeah. Okay. So, right. I have two things, right? So I have, let's see, I have this lemma. And using this lemma, I want to prove two lower bounds. One of them is a lower bound for this online bounded space hypercube packing. And the other thing was this price of anarchy lower bound. And I'm just saying, I will not say this in detail, but to produce this instance, to prove a lower bound for this online bounded space hypercube packing problem, I have to produce some instance that shows that any algorithm will do badly, right? So I was trying to describe this instance. And yeah, what is an instance? Yeah, it's a sequence of these cubes, right? And I just say, well, you put many of Q2s at the beginning. How many? As many as you see here on the picture on the left. And then you put many Q3s. How many? As many as you see here on the picture on the left. But of course, you just give individually little cubes, right? Many Q2s, many Q3s, and so on. And then if you think a little bit, the online, because of this bounded space, it will have to produce this picture on the left. It cannot do better than producing something like this thing on the left. But on the other hand, the offline optimum is more like the right, or at least is at least as good as the right. So yeah, I'm not sure it's understandable, but again, you use the fact that these many cubes can be fit into this packing U, and you kind of try to exploit it.
Actually,
Does that make
while
sense?
we're on this slide, can I ask a question?
Yes.
So you compare with absolute optimum, but now you suppose you compare with optimum when items arrive in the same order. You have to keep the same boundedness condition, but you know them in advance, all at once. So like
what do I know in advance?
So you know all items in advance, but they arrive in some order, and you put them in bins, but you keep open the same number of active bins. Do you get the same
So
gap?
actually, oh, I see. So you're asking about a variant. So again, what do I know in the variant? Oh, I see. So it's
both have
offline,
the
but
same
bounded
number of
bins.
active.
But I have to act on each element. Yeah, actually, I don't know the answer, but you have to act on each element of the sequence in order.
Yeah,
you're asking.
And keep at
I
each
just
time
know what happens
the
in the
same
future.
number of active bins. Just curious.
So it sounds as though you might as well tell the adversary in advance exactly what your sequence is. And as long as the number of open bins is bounded, you still won't be able to do any better.
Yeah.
That's okay, just a question that came to my mind.
Right. It doesn't, yeah, right. Yeah, very good. So we are not using the fact that you don't know. It's just that I have to, right. I think I agree, right. Thank you. Good. So let's see. So let me just say a little bit about the packing lemma. So the point here is that our cubes, our QKs, have side length slightly more than 1/k, and it's easier if you say the side length is 1/k times 1 plus epsilon. So this is how much a cube would take. Here is 1, 1. So if you kind of keep stacking them, so this is the k minus first, and when you put the last, kind of it would overlap, right? Or you would fall out of the bin. Anyway, so there's an overlap between the k minus first and the kth guy when you stack them up like this. So that's the problem. Good. But anyway, I want to put the cubes according to this grid, so to speak. So, and also I want to label these things. So I will have label 1, 2, up to, this is label K. So again, 1, 2, and K is here. This is K. Now, this cube here is a copy of KK, which has base point 2 and 2 in coordinates I and J. So so this picture is 2-dimensional, but it's kind of a projection, the IJ plane, but I have D dimensions, right? But anyway, so this cube here, I could denote by Q dot 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 2 in coordinate I, J, 2 in coordinate J, and so on, because it has this base point 2, 2. Sorry, here is 2. On the left is 1, 2, 3, and so on. Okay, now this guy here has base point 1. So here is 1 and K. This guy is 3, 1, 2, 3 here on the x-axis or I-axis. K coordinate K minus 1. Note that these two, I cannot put them in the same column, right? So this coordinate K and coordinate K minus 1 are incompatible. I don't like that. Okay, let's carry on. So the previous picture kind of tried to say something like the following. If I have this some word in 1 dot 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 to K to the D, so brackets K to the D, I can associate some placing of this QK in the hypercube, in the unit, in the bin, right? So there's some association between these code words and geometric placing. Okay, so what we want is a family of code words LK, subset of brackets K to the D, such that if you consider the family of the geometric cubes, right, they form a packing. That's one thing I want. For each K, I would like to specify such an LK. Also, I will want the LKs to be pairwise compatible. And I want this for all Ks up to S, which is of order D over log D. And the fact is that you can achieve LK at least 10 over 11 K minus 1 to the D for each K. And the kind of the combinat, so we translate this to this following two combinatorial things. You can impose these combinatorial conditions here. So the first one maybe is the following. So you see, for every coordinate I, so it's a cheap way of avoiding K minus 1 and K at the same time. So I don't know, in this picture, I said that you cannot have this, right? So you cannot have this guy and you cannot have this guy. So in this coordinate J, this is K minus 1 and this is K, right? You don't want to have that in coordinate, in some fixed coordinate, in this case, coordinate J. So that's it. So for every I, you decide to avoid either K or K minus 1. That's kind of not bad because you're trying to kind of write these element of brackets K to the D. And in each coordinate, you say, well, I avoid K or K minus 1. That's still good. That's still K minus 1 to the D possibilities, right? Okay, so we do that. Now, the second condition is the following. Now we are mixing, so here, now we are mixing what we are doing with QKs and QLs. And here I'm thinking L is less than K. Right, it's not so, okay, so how do you make sure that some copy of QL and some copy of QK don't match, don't intersect? One way is to do the following. So this is the picture, this is the grid for K, right? The grid for L, which is less than K, it's so the cubes are bigger, right? This is 1QK. If you take QL is bigger, so this is 1QL, this is another QL. It will leave a space like this when I stack L minus one of these QLs. So this QK here, which is really at the top, will be disjoint from the guys in the bottom. Yeah, I'm not sure whether this made so much sense, but so this is the combinatorial condition that you require. Now I'm running out of time. So now the game is to produce these LKs, large LKs. And what we do is the following. We first use this lemma 7. This is a simple fact. I mean, this is about the family of sets. So you produce a family of sets, each set of size d divided by 2. And you require their intersection, pairwise intersection, to be less than this. So if you have sets of size d over 2, you expect the intersection of 2 random ones to be of size d over 4. And 7 over 26 is slightly bigger than 7 over 28, which is 1/4, right? So you can achieve this very easily, randomly, for instance. Okay, so you use this family of sets. And then when I produce, I'm trying to produce LK. And remember that when producing LK, in every coordinate, I want to avoid uniformly coordinate k minus 1 or coordinate k, right? I do the following. So if this is no, not fk, if this is some fi, some member of the set system, oh, I'm sorry, it is fk. If this is the fk member of the set system, I just say, well, here in these coordinates, I don't want k minus 1. And in the other ones, I don't want k. Right, and then again, oh, I'm sorry. And then again, if I have some FL, so you use crucially that FK has some coordinates outside FL, and you kind of force this guy to be K, and this guy, it's not L. Anyway, right, so this is how in some fixed coordinate, you avoid intersection between members of LK and members of LL. Right, I'm sorry, I should stop here. So there's some calculations here. So again, what we did is that for this Beampacking problem, online bounded space Beampacking problem, we know the difficulty of the problem is d over log d. In this game version, in the game problem, there's a huge gap, and I think it would be nice to investigate this more. Thank you very much. I'm sorry, I'm out of time.